Welcome back. You might have wondered why honey is more viscous than water. Well, honey contains sugars such as glucose, and they're larger molecules than water. And they also contain multiple polar hydroxyl groups that can undergo more hydrogen bonding between adjacent molecules. So, therefore, honey is more viscous, flows less easily than water. And we'll look at that, why that occurs in this lesson. So in this lesson, we're looking at naming and properties of organic compounds, part 2, and we're going to look at revise what we know about intermolecular forces. We're going to look at the physical properties of boiling and melting point and also viscosity, linking that back to structure and bonding. So you remember from year 11 chemistry that we have different types of intermolecular forces. And this is a diagram that we had in year 11 chemistry course. Intramolecular or covalent bonding is very strong. So that's very strong bonding. And then of the intermolecular forces, hydrogen bonding is the strongest type of intermolecular force, followed by dipole-dipole attraction. And the weakest type of intermolecular forces are dispersion forces. Now, all molecules have dispersion forces between adjacent molecules. If we have a small molecule, it has a low boiling point. And as molecules get larger and larger, they have more and more electrons in them. The bigger a molecule, the higher its boiling point, because there are more dispersion forces between adjacent molecules. The more electrons a molecule has, the greater the possibility that an instantaneous dipole will form, which will induce another instantaneous dipole in an adjacent molecule. Now, the only types of intermolecular forces between alkanes and alkene molecules are dispersion forces, because alkanes and alkenes are nonpolar for two reasons. There's very little difference in electronegativity between carbon and hydrogen atoms, and alkanes and alkenes are quite symmetrical. Dispersion forces increase with an increase in the length of the carbon chain. They also increase with less branching, so less alkyl groups coming off the side of the parent chain. And they also increase with increasing saturation, so less carbon-to-carbon double bond kinks in the chain. The next strongest type of intermolecular force are permanent dipole-dipole attraction. So permanent dipoles are molecules that have polar bonds and are asymmetrical, and dipole-dipole attraction is a stronger type of intermolecular force than a simple dispersion force. The strength of a permanent dipole-dipole attraction depends on the difference in electronegativity of the atoms in a covalent bond. And you can remember that Fonkel is the order of decreasing electronegativity. So fluorine is more electronegative than oxygen, which is more electronegative than nitrogen, which is more electronegative than chlorine, which is more electronegative as we go down the group of the halogens. So this pair of shared electrons is spending all of its time near the more electronegative atom. So that's delta negative, a partial negative charge. And the electrons aren't spending any time permanently next to the hydrogen, so this end of the molecule is slightly positive. And if we have a slightly negative and a slightly positive, the electrostatic attraction will be a dipole-dipole interaction or attraction. So dipole-dipole attraction can occur between these types of groups in functional groups in organic molecules. Aldehydes, which have got the CHO bond on an N carbon. Ketones, which have the carbonyl group somewhere in the middle of the molecule. esters, which also contain the Cook group, but they contain the carbonyl group as part of that Cook group, and haloalkanes, where we have a polar carbon to halogen bond where X represents a halogen. So here we have two ketone functional groups. The oxygen part of the carbon to oxygen double bond. The oxygen is the electronegative atom. There's 4 electrons in this double bond, and the 4 electrons spend all their time near the oxygen, making this part of the bond delta negative, and the electrons are withdrawn from the carbon, making this side delta positive. Delta positive will attract delta negative and vice versa. So we can have permanent dipole-dipole attraction, and we show intermolecular forces using dotted bonds. The strongest type of intermolecular force is hydrogen bonding, and it's also the strongest type of dipole-dipole attraction, but it has its own name because it's particularly strong. Hydrogen bonding can take place between a hydrogen that's bonded to a fluorine, oxygen, or nitrogen atom on one molecule, and a fluorine, oxygen, or nitrogen atom on an adjacent molecule. So a good example of hydrogen bonding is between water molecules. So the oxygen part of water is more electronegative than the hydrogen. The oxygen part is delta negative. The hydrogen part is delta positive. And delta negatives attract delta positives. And so water molecules have hydrogen bonding in between them. So apart from water having hydrogen bonding between adjacent molecules, the following organic compounds also experience hydrogen bondings between adjacent molecules, in addition to dispersion forces. So amines and alcohols, because of the highly polar nitrogen to hydrogen and oxygen to hydrogen bonds. Carboxylic acids have got the highly polar OH bond, but they also have dipole-dipole attraction between adjacent carbonyl groups. Amides have the highly polar NH bond, which is part of the CONH, but also permanent dipole attraction between adjacent carbonyl bonds. So we could have another carbonyl. And here we have some amide molecules, and we've got hydrogen bonding between adjacent molecules. Now we're going to look at some of the physical properties that are influenced by the type of intermolecular forces between adjacent molecules. The first two physical properties we're going to look at are boiling and melting point. So these are physical properties that are affected by the size and the shape of molecules. Molecules within the same homologous series, that means a family of molecules that differ by CH2, they have, as the carbon chain gets longer, they have increasing boiling and melting points with the addition of CH2, because there are more electrons, resulting in more dispersion forces between adjacent molecules. So the strongest intermolecular forces between alkane molecules are dispersion forces. And here we can have some structural isomers of C5H12. We can have pentane, methylbutane, and dimethylpropane. Now, pentane has got a higher melting point than methylbutane, which has a higher melting point than dimethylpropane. And it all comes down to the shape of the molecule, because these are structural isomers. This is a linear shape. This has got one branch, one methyl group, and this one has got 2 branches. Now, if we have linear molecules, they can stack on top of each other and have dispersion forces between the molecules. So there's more dispersion forces, which means a higher melting point. The dimethylpropane has the lowest melting point of the three molecules because it has the most branching, and so fewer possibilities of dispersion forces. Getting back to what we started talking about at the start of this lesson is viscosity. So viscosity is the resistance for a fluid to flow. Water is a very small molecule, and adjacent molecules, although they have hydrogen bonding between them, is a relatively low viscosity. If we start looking at cooking oils contain triglycerides, which are very large molecules that have many dispersion forces between long nonpolar chains, in addition to dipole-dipole interactions with adjacent ester groups. They have intermediate viscosity. So if we got a teaspoon of water and a teaspoon of oil and we tipped the substance off the teaspoon, we would see that the oil would appear to be more viscous than the water. But in comparison with water and oils, if we get a spoonful of honey, we notice that honey is the most viscous. And it's because honey contains sugars, which are monosaccharides and disaccharides, which are relatively large molecules with lots of polar hydroxyl groups. And adjacent hydroxyl groups can undergo hydrogen bonding, which means that we've got multiple sources, multiple locations for this hydrogen bonding. And we show the hydrogen bonding as a dotted line between adjacent molecules. And that contributes to honey having a higher viscosity than oil and water. So let's summarise what we've learned, and some of this you might want to put on cue cards to remember. So hydrogen bonding occurs between amines, adjacent amines, alcohols, carboxylic acids and amides. Hydrogen bonding is the strongest type of intermolecular force. The next strongest type of intermolecular force is dipole-dipole attraction, and that occurs between adjacent aldehydes, ketones, esters, and haloalkanes. The weakest type of intermolecular force are dispersion forces. Alkanes and alkenes, the only type of intermolecular force between adjacent molecules, are dispersion forces. And remember, dispersion forces occur between all molecules. They increase with the length of the carbon chain. They increase with reduced branching, so less alkyl side chains, and increased saturation or less carbon-to-carbon double bonds or kinks in the molecules. Melting point, boiling point, and viscosity are physical properties that increase as the strength of the intermolecular bonding increases, is highest when hydrogen bonding is present between adjacent molecules, is medium when dipole-dipole attraction is present between adjacent molecules, and is lowest when dispersion forces are present. Remembering that if we have a homologous series of compounds, the smaller the molecule, the lower the boiling point, the melting point, and the viscosity. As molecules get larger, there are more dispersion forces between molecules, resulting in a higher boiling point, a higher melting point, and becoming more viscous. What's coming next is Chapter 7, Progress Check. So I'll see you then. Bye.